So the first presentation is a keynote. Yeah, okay, the podium is yours. Please use your 25 minutes.
Thank you, Chairman. Good afternoon, ladies and gentlemen. It's my honor to share some research we have done in Taiwan about earthquake and seismic protection. And the title of my presentation is Development of Ground Motion Characteristic Prediction Module for Intelligent Isolation System. My name is Lin T. I'm a professor from National Chiao Tung University in Taiwan. In today's presentation, I will first give a review about why we start this research, the background of this research, and the flowchart of this research. And you can see in this research and in this presentation, it's mainly divided into two parts. The first one, I'm going to share you one ground motion characteristic prediction module. And by utilizing this module, then we develop a GA fuzzy control law to control the response of the structure. Definitely, we need to verify its performance. And finally, I'll give you some summary and conclusion. We all know that earthquakes have a large impact to our daily life. And as you can see from these pictures, especially for people who live in the Pacific Rim, we almost every day have earthquake. It would be called to major earthquake or minor earthquake. And when we suffer from major earthquake, some of the building may collapse. This is two cases in Taiwan, and you can imagine the difficulty of the people inside. They may lose their life, they may lose their property, and the building just collapse. And another issue we always face in Taiwan is famous for high-tech industry, especially for semiconductors. So you can see this industry or this factory, they are vulnerable to earthquake too. If these devices or this industry is impacted by earthquake largely, and the whole economy of the country may also be damaged. And recently in Taiwan, there's a very hot issue called earthquake early warning. So I want to especially mention that the earthquake early warning is not for prediction, but the idea of that one is once the earthquake happens, when the wave propagate to your building, they may be 10 minutes, 10 seconds or 20 seconds or even 30 seconds of time lag, and we try to warn you before the major wave strike you. That's called earthquake early warning. So in this study, we try to utilize this concept and combine it with structure control. I want to talk about the structure control first. Structure control could be mainly divided into three categories. There would be active control, semi-active control, and passive control. You can imagine the most popular one actually is passive control. That could include we call them viscous dampers or steel dampers or bracing. They are all called passive devices. But these devices could only provide up to maybe 50% of the reduction percentage, means that it's very economic, but the performance is not that well. If we want to get a very high performance, then we should choose active control that's operated by hydraulic actuators. And there's another problem, that is these devices or these systems may not be very reliable. They may even destroy your building before earthquake. So in the last decades, people started to develop a system called semi-active control, and we are going to use the concept and develop a semi-active control system. This system should utilize to merit the advantage of active control and passive control. So this is the flow chart of this study. In the first part, we try to collect as many ground motion database from the world, as many as possible, because we want to demonstrate the concept of big data. In the second one, we utilize this data to develop the ground motion prediction module. The ground motion prediction module itself is trained or developed based on a branch of artificial intelligence that's called support vector machine or support vector regression classification. If we could predict the characteristic of the ground motion correctly, then we can utilize this one to develop the control law. And we will use the platform we are going to utilize, or we call that the hardware we are going to utilize is called LSCIS. I'll introduce you later. And this finally we'll do some numerical simulation. Let's first talk about ground motion characteristic prediction module. We try to, as I mentioned, we try to collect as many database as possible, as many earthquake time history, as many as possible. And finally, we find there's a good candidate. That is the Pacific Earthquake Engineering Research Center, we call PEER in the United States. They collect a lot of database, and also one thing very important is they already classify them as near fault earthquake or far field earthquake, because these two categories has totally different characteristics. So in this database, we choose 132 sets of ground motion, including 78 sets of near fault earthquake and 54 sets of far field earthquake. You may have a question, say, but the number is only 132. Why is that so small? Because as I mentioned, if you want to do earthquake early warning, one very important issue is you need the vertical direction time history. That's why this issue has been important for only the last maybe 20 years. So when we want to collect the vertical direction measurement, we can only have 132, but comparatively, this is a big number already. And then we do some literature review. Scholars say if you want to make your database diverse, you want to increase its diversity, you need to especially care about some characteristics. That's on-site geological condition, distance between station and epicenter, fault rupture mechanisms, rupture directivity effect, and so on. So these six concepts or these six factors were mentioned by the scholar, but we want to quantize that one. So it needs to be described by indicators, or we say parameters. Based on the system or the earthquake early warning system we developed in Taiwan, now we use 6 indicators to predict the intensity, pick a PGA value, the peak ground acceleration value by 6 indicators. I list that one in the first 6 one, and the detail I'll show you in the next slide. And we additionally add 2 parameters because, as I mentioned, we want to predict the characteristic of ground motion, not earthquake. So we add 2 additional parameters related to the energy of acceleration and the energy of velocity. So preliminary study shows that if that's a far field earthquake, the value would be relatively small. If that's a near fault earthquake, then the value would be very large. This slide or this diagram shows that it's possible to develop a ground motion characteristic prediction module based on the 8 indicators we selected. And this is the list of the 8 parameters. They are the peak measurement of ground motion, ground acceleration, peak measurement of ground velocity, peak measurement of ground displacement, effective predominant period, and integral of square velocity. One thing we need to be very careful is these parameters are calculated only from the first 3 seconds of the earthquake, not the whole time history. So that's what I mentioned. Based on the 3-second early arrival wave, we should be able to predict if that's a near fault or far field earthquake. Then we define the outcome. Here, we need to separate the result of near fault and far field earthquake. So we propose this equation. You can see XIN is the average value we have for near fault earthquake, the average value. And another one, XIF, is the average value we calculate from the database for far field earthquake. And this equation could enlarge the difference of near fault earthquake. If that's a near fault earthquake, by using this equation, then that could be enlarged extremely to a very high value. If that that's what we call an F ratio. Okay. So for the database, we select 75% of the sample as a training sample and 25% as testing sample. The input parameters are the 8 indicators I just mentioned, and the output, they are the NF ratio we define. The output would be 3, 2, 1, and 0, -1, -2, -3 for 7 levels. So by using this one, we should be easily to identify if that's a near fault or far field earthquake. This is a result. You can see the test result. We try a lot of different support vectors, and the best structure for the support vector classification would be quadratic one, and it could reach a very high accuracy. That's 91.7%. And this, if that's shown in green color, means it's 100% correct that I could indicate it. If that's in the pink color, means there's a slight error. This is a percentage. You can see in the diagonal direction, almost it's perfect, means that the prediction module could identify if that's a near fault earthquake or far field earthquake. But for some area, they have a slight difference. But remember that the error would be plus or minus 1 level. Means that for this one, it could be original would be -2, but my result would be -1, only 1 level difference. It's not a huge error. So we think this maybe, or I should say the high successful accuracy rate give us a strong support for us to develop the control system. And third part, I'm going to talk about how we develop the system. That is the GA fuzzy control law. For the last 10 years, we cooperate with Professor Liu from National Cheng Kung University in Taiwan, and we propose the leverage type stiffness controllable isolation system, which is abbreviated as LSCIS. And this structure, as you can see, it's very easy to manipulate because it only have a very simple leverage mechanism. And second issue, it only needs a feedback of displacement and velocity. I only need to measure the displacement and velocity of the structure, then I could easily control its response. And this slide shows you the idea or theory of the system. The green one is the pivot point. It can move to the right-hand side and move to the left-hand side. If it moves to the right-hand side, then the leverage will be changed. The different lengths of this side and this side could control the stiffness of the system. You can see if the pivot point, if moved to the right-hand side, it could increase the corresponding stiffness up to 50%. If it's moved to the left-hand side, then to the minimum value, it could even reduce the stiffness to only 20% of its original stiffness, which means that during the time history of the earthquake, if I could properly switch the pivot point right-hand side or left-hand side, then I can control the response of the structure. And in the last 10 years, of course, we gradually developed several systems. The first one is called LIEM. It cares about the kinetic energy only. And the second one is called minimum energy wetting system. It considers the kinetic and potential energy. And recently, because we start to develop the earthquake early warning system, so we propose a feed-forward predictive earthquake energy analysis FPEEA system. This one could preliminarily detect the percentage of near-fault earthquake or far-field earthquake. But in this study, we try to improve the third one and propose a new one. Okay, I tried to go through quickly about the idea. If you want to control the structure, you should indicate, we call that the criterion or performance index. You can see it's composed of kinetic energy, potential energy, and the third one is the people restriction parameters. And previous study shows that the potential energy actually is very important. So if you differentiate this criterion, you can calculate the optimum corresponding or as an optimal increment of stiffness, and you could switch the pivot point. But the version of FPEEA we propose is that we further divide the weighting of potential energy into two parts. One is contributed by near fault earthquake, and one is contributed by far field earthquake. So you can see the equation is slightly changed. The result is that if you could identify the C1 value, which is related to near fault earthquake, then everything is solved. If the prediction is correct, then it could reach the optimal control performance. Okay, so this is what we do. We try to connect the NF ratio we have and the PGA, peak ground acceleration we predicted, connected these two parameters to C1 value. And here we introduce genetic algorithm for optimization. The control target itself is we use for the near fault earthquake, because we found that we investigate it have a very large isolation displacement. So we need to focus on the isolation displacement, try to suppress its most. And for far field earthquake, it have a very high response on superstructure acceleration. So for far field earthquake, we should focus on these parameters. These are the number. The number means what we have from the peer database. We use a lot of different earthquake records and try to optimize its value, try to find the optimum C1 value. And the optimization process was conducted by genetic algorithm. These are some some parameters we have for the genetic algorithm. The population size is 100 and the parent selection is rowlet, for example. And this is a process. You can see the fitness value decrease gradually, and to the constants means the process, the genetic optimization process is finished. And this is the result. The C1 value, when you have a very different NF ratio, or you have a different predict PGA value, then this system could show you a different C1 value. Remember I say once I determine the C1 value, I can substitute it into the control criteria, then that can control the structure properly. But we are not satisfied with this result because you can see it's a bar chart. Then we use fuzzy inference system to smooth size it. So everything now is smooth, means that no matter which value you have for the NF ratio, no matter which value you have for the predict PGA value, you could easily indicate the corresponding C1 value. Okay. Now I'm going to show you the control effectiveness verification, that is to verify if the system could work in real life or not. Remember what I say is when there's an earthquake, then the system is ignited and I predict the characteristic of the ground motion and decide the PGA value, NF ratio, and finally decide the C1 value and make the control to the structure. We make an overall evaluation, that is for the data we collected of near fault earthquake. You can see the proposed method we call the GA fuzzy. They have a very good result, especially for isolation displacement. It have a very high percentage of better result, means the proposed system could be better than passive, LIEM, MEW, and FPEEA. And also if the system face a far field ground motion, then the control target should be switched from isolation displacement to superstructure acceleration. And you find that the percentage of better result is also very high, means that it could have overall advantage by using the system we proposed. Okay. Finally, I'm going to show you some time history for the comparison between the GA fuzzy system we proposed and with FPEEA. This is a very famous earthquake. This is a very famous earthquake in Taiwan. We call that is TCU 065. I show you the acceleration, velocity, and displacement. So in general, I show you the maximum value. You can see this is a near fault earthquake, so we care about the isolation displacement. If I introduce a passive control, its control would be benchmark, so the ratio to be 1. And the LIEM could reduce its ratio for 13%. MEW could reduce the ratio to be 34%. And in our system, we can even suppress or alleviate it to 46%. That's a very high percentage. And this is the time history. The acceleration, you can see the acceleration of the superstructure could be suppressed effectively, and also the isolation displacement could also be suppressed significantly, because the blue one is FPEEA and the orange one is GA fuzzy, is the system we proposed. And finally, this is the pivot point displacement. This is the movement of the pivot point, and this is hysteresis loop reached by the two different systems. Finally, I'm going to wrap up my presentation. You can see in the first one, we proposed a ground motion prediction module, and the proposed support vector classification could have a very high accuracy to 91%. And of course, the system could work in the first 3 seconds, then it will switch the control parameter for the LSCIS system promptly between near fault earthquake or far field earthquake. And we utilize a lot of branch of artificial intelligence, including genetic algorithm, support vector classification, and fuzzy logic. And finally, the result shows us that the proposed system could outperform other control law. And in the next stage, now we are conducting the experiment in Jiao Tong University. And I hope we can verify that one and show you in the next presentation. Thank you.
Thank you very much for your very interesting presentations. So please, questions. We have a couple of minutes for questions.
Can I have?
Yes, please, Professor Kuznetsov.
Yes.
Dear Professor Lin, thank you very much for an excellent presentation. And I have a couple of questions. The first one, what is the average time discretization, say milliseconds or something else, needed to control systems, semi-active or active systems? What is your opinion?
Can I ask it now?
I mean the time discretization.
Yes. I'll ask the question now, right?
What is the average time discretization needed for active control systems or semi-active control systems to get information?
Yeah, thank you, Professor. This is a very good question. I think for active control, because it's controlled by hydraulic, so that could be milliseconds. And for the system we have, I think now it's about, based on my experience, that could be 10 milliseconds. That's for a semi-active control, because in our system, the main consideration is we don't want to use a lot of energy to control the pivot point. So it cannot move very fast when compared to active control. But I would say we have, like I mentioned, for the last 10 years, we have developed this different generation of the control system. And basically, in the experimental verification, it works pretty well, very close to numerical simulation. So I think the time we need for operation, or I should say the time lag, doesn't affect the performance of the system seriously.
Thank you very much. And if possible, can I have another question?
Sure.
The other question is that from modeling natural piano systems, it is known that for electronic piano system, there is need in not only displacement information, but velocity, acceleration, and possibly third order time derivative to just precisely control what can be happened when the pianist puts on the particular key. So presumably for controlling systems, you need to know not only initial displacement, initial velocity, initial acceleration, but possibly you need to know like third time derivative, where it's enough.
You mean control, right?
Yes, yes.
Yes, I'm sorry, because due to the time, maybe I didn't explain it very clearly. When I'm doing the control, actually, I need to measure the response of the system, or I should say the structure. That's what I mentioned. I need to measure the displacement or velocity, but that's not only for the initial value, but I need to measure the whole time history. And for every time step, our system or our algorithm will calculate the optimum pivot displacement and send the command to the pivot to switch to the right position. Yes.
Thank you very much.
Okay. Thank you very much. Unfortunately, me myself, I have a couple of questions, but I keep that for the next occasion, probably when we see next time. Thank you very much once again.